Hi, in this video, we're going to take a closer look at the IPv4 routing table. So a lot of this information originally came from a book called Cisco IP Routing by Alex Zinnan. It's an older book, but it's a great resource still if you want to get a understanding of kind of the internals of Cisco iOS routing processing and packet forwarding, kind of a different look than just how to configure routing. Okay, so that's just a shout out to Alex Zinnan. Okay, so the Cisco iOS routing table. This all originated because of the days of classful IPv4 addressing. So when you received an address, you received either Class A, Class B, or Class C address. And you got the mask either /8, /16, or /24. And when you received that address, you got the whole thing. So if you received a Class B 172.17.00/16, there was nobody else that had 172.17. That was all you. And all the subnets and all the host addresses underneath it was all you. And that we moved from classful to classless back in the 1990s. Classless meaning that addresses were no longer allocated like this. You received a specific network address, and a specific mask that could be anything, could be a /19, /26, /27, whatever, based on your justification, how many host addresses you could actually justify that you needed. But the IPv4 routing table is still based, the format of it, on the days of classful addresses. So if we look at an IPv4 routing table in iOS, we see that it has a classful structure. And this affects not just the structure of the routing table, the classful addressing, but also a little bit on the lookup process. So bear with me as we go through this. First of all, there's a level 1 route. And a level 1 route, and we'll see level 1 routes are the ones on the left here, the ones that are not indented. I'll talk about these indented routes, which are known as level 2 routes or child routes. But the ones that are indented are level 1 routes. I'm going to look at the ones that actually, the ones in red here specifically at first. These are known as level 1 ultimate routes. These are routes that actually have an exit interface next hop address. Yep. For example, actually this one here should be in black, but that's okay. So level 1 routes, here's a level 1 route here. Here's a level 1 route, level 1 ultimate route. These are level 1 ultimate routes because first of all, they have a subnet mask that is equal to or less than the classful mask. What does that mean? 192.168, that's a Class C address. Class /16 is less than the Class C mask of /24. Okay, 192.168 is a Class C address. In the classful world, /24, /16 is less than that. And this is a ultimate route because this is a network that was learned, a specific network, and this is the network itself, and it was learned via this next hop and exit interface, so it's all in the routing table together. This default route can also be considered a level 1 ultimate route. This sounds a little confusing. Hang in there. We're going to get there. We're going to explain all this in just a moment. Okay, what about other level 1 routes? Well, in blue here, the other two, these are level 1 parent routes. Notice with these routes, there's no next hop or exit interface here. These are really just headings for what comes below it. It says that all of these networks, which do have exit interfaces and or next hop IP addresses, these are routes that are actually learned, either directly connected or through a dynamic routing protocol like RIP. These were the networks that were actually learned. It just so happens they all fall under this heading. Okay, and what heading are we looking at here? Okay, this heading is, this is a level 1 parent route. It's a class B/16. Okay, and it says variably subnetted because the different networks it learned about have either directly connected or RIP have different subnet masks. We'll see an example coming up that if all of these are the same, then it would actually put that subnet mask here instead of the /16. All right, but these are just headings. Okay, they're not the actual route themselves, although they are part of the lookup process. Okay. So a level 1 parent route, there we go, it indicates that there are some level 2 routes known as child routes. And it's those child routes, the ones with a subnet mask. A child route is a route that was learned with a subnet mask, let's go this one here, greater than the classful mask. So /24 is greater than the classful mask of /16. So the child route was entered under the automatically created parent route. Same thing with these down here, 209 networks, RIP directly connected. These are all class C networks, but they have /30s. And so they all fall under the parent route, and the parent route is shown here, the classful route. All right, I'm going to explain why this was done in just a moment. Let's continue here. Okay, so the idea here, and this will make more sense in a moment, so let me just kind of go through this. If we were sending a packet to 172.34.1, it would search the routing table for an ultimate route. In this case, it found a parent route. So the parent route 172.30.00 is a /16 class B network. Okay, 172.30 is a /16, a class B address. This /24, why it shows /24 instead of /16 is because in this case, all 3 of these child routes are a /24. So it will show if all the child routes have the same mask, that mask will be shown here instead of a /16. But what gets matched first, and we'll take a look at this more in a moment, is it first does a match on the parent route, the heading of 16 bits, and then looks for a 24-bit match with one of these. If it finds it, it will use that route. Otherwise, if it doesn't find, if there is no match, and there isn't in this case, 172.34.1 does not match any of these child routes. There's no 24 bits that match these 3 routes. So in this case, none of these match, and actually in this case, it will use the default route because 0 bits have to match here. Best way to kind of understand this, let's look at some examples. Okay, but first let's understand the routing table lookup process. And when an IP packet comes in, and this is true for IPv4 and IPv6, the destination IP address is looked up in the routing table. The best match depends on, we're going to see in a moment, but what it looks up is the network address and the prefix length. The prefix length is going to say how many bits must match the prefix for this to be a match with the destination IP address. All right, let's take a look here. So what if we had a packet with the destination IP address, the IPv4 address of 172.16.0.10? And what if we had 3 routing table entries? And what if all 3 of these happen to match the destination IP address of the packet? For example, route 1, it says 12 bits have to match, and yep, 12 bits match. Route 2 says 18 bits have to match for this to be a match. And guess what? 18 bits do match. But Route 3 says 26 bits must match. And guess what? All 26 bits do match. So Route 3 would be the longest match, the best match. It would be the route that is used. All right. That's what I'm just saying here. All right. So let's take a look. We get a packet with the destination IPv4 address 192.168.1.100. Let's look for a level 1 ultimate route. And that's a route that has not indented and has an exit interface next hop. And there's none to choose from here. Okay. There is, but we're going to see that there's a level 1 route, a parent route, that is a better match. So here we have actually 2 level 1 routes that match. We have this RIP route here that matches. 16 bits must match for this to be a match. But we also have another level 1 route here that matches. But 16 bits is better than 0 bits. So that's why we're going to use the RIP route here, because 16 bits match. That's the longest match. So it's going to use this routing entry, the next hop exit interface, to forward the packet. What if we have a destination IPv4 address of 172.16.3.10? Okay. Well, in this case, there's no ultimate routes that match, but we do have a parent route that matches right here. Okay. It's a parent route. It doesn't have an exit interface or next hop address. It's just a header for the child routes. So let's see if there's any child routes that match. So now it's going to search the indented routes, and it finds one that does match. The best match is 172.16.3.0/24. 24 bits of this routing entry match the destination IPv4 address. So we'll use this route to forward the packet. Okay. What if it had a 172.16.5.10 as the destination IPv4 address? Well, again, it says I have a match with a parent route, a level 1 parent route. These 16 bits match. However, there's no child routes that match. Okay. Well, we'll go there in a second. So none of these child routes match. Okay. We need 24 bits of this to match, 24 bits, 28 bits, and there's no match of any of these with this destination IPv4 address. So in this case, it will then continue to search a level 1 route, and there we find a default route. So it will forward it using the default route because 0 bits need to match for that to be a match. Okay, how about 10.1.2.3? Well, in this case, there are no level 1 ultimate routes to choose from. There are no parent routes to choose from. So in this case, we're going to use a level 1 SuperNet route, the default route, which has the longest match because 0 bits need to match. And that is the gateway of last resort. Okay, what if we have 10.1.2.3 again, but look, no default route this time? Well, no default route, no ultimate 1 route, nothing matches. So in this case here, because nothing matches, the packet will be dropped. All right, so I hope this helps you understand a little bit about the structure of the IPv4 routing table and the lookup process. As you'll see, IPv6, much easier.